Hello and welcome to the vertical transfer tutorial. We're going to do this tutorial by using Fluent, ANSYS Fluent. The geometry we're going to use, this is a Y-shaped pipe. So that means we have one inlet and two outlet. I already uploaded the Y-shaped pipe in UTS Online, so you can download it and you can just import the cut into this Fluent. So if you see here, the geometry is already updated. So what I will do is I will click on mesh. You can see the mesh window here. This is our Y-shaped pipe. If I rotate it, you can see some domain here which say this is actually the pass, different pass. So this is the first section and this is the bifurcations. You can remember what actually you need to do before the meshing. You need to do some name selection. So what I'm going to do is I will put this name, maybe this is the inlet, so I will type this is inlet and this is outlet. So let's say this is outlet 1 and the other one, this is outlet 2. So this is outlet 2. So we have done the name selection of the inlet and outlet, and now we're going to do the name selections for this wall. So I have selected wall surface except inlet and outlet. So let's say this is the wall. So we have done with the name selection. I will do, you know how to do the meshing, you know some advanced technique for mesh generation. So I'm not going to show you how to do the mesh again, but we need some mesh. So what I'm going to do is I will just generate some basic mesh, not some advanced meshing. So definitely we're going to use the CFD and the Fluent mesh, and what I will do is I will just check here. Okay, I will keep the other setting as it is, and then I will click on generate mesh. So then you see how it goes. So you can see we got some this basic mesh. So I'm not going to refine this one because this mesh, this is just for demonstration purpose. If we generate some fine mesh, it will take a higher computational time. So to avoid this computational time, I'm going to use this mesh. But the important thing is when you will do some meshing, especially for the vertical flow, don't forget to generate the inflation layer. We actually want to create the inflation layer on this wall. So click on this name selection, select on this wall. You see the program control inflation is exclude, so include this one, and then go to mesh. See, this is the inflation, and go out. Say this automatic inflation is program controlled, and maybe you can use maybe 10 layers. So once you have these 10 layers, click on generate mesh, and I think it should be quick. Yeah, so this mesh, it is actually not good, but if you see here, this is our inlet. So this is the the inflation layer we have. It looks quite good, the inflation layer, but we need to do some refinement. If you want to check the cross-sectional view of the mesh, then what you can do, you can create some section plane from here and you can cut it like this. Then you will see this is the interior view. So, okay, so we have done with the mesh. As I said, we're not going to refine it, but you can check the quality of this mesh. So the minimum, we will check the minimum orthogonal quality. So this is the orthogonal quality. Honestly speaking, this is not good. It should be much better, the quality, and all the range of the minimum and the maximum orthogonal quality. Actually, you see here it is not good, but definitely you see here it is not good. So we have very fine mesh here, especially for this section. But what I say, this is just for the demonstration purpose, and I'm making this video. If it takes long time that we can't run the simulation, the video will be lengthy. So that's I have decided to use this mesh. So we'll assume that this is a good mesh. So I'll close this one now, and I'll click on update projects. So you can see the mesh is already updated, but if you are using Workbench, then you may get this error actually that update failed for the solution component. We haven't done anything with the solution component, so you can simply just ignore this error, click on OK, and you can just remove this section. So the mesh is updated, so just ignore that error. So click on setup now. It should be double precision as it is. We want to display the mesh after the reading. Yes, this is 3D, so click on OK. So if you click on OK, then we have this window. So we have kind of 21,000 mesh. So it is asking about some basic informations, so just click on OK. So if you rotate it, you can see all of your mesh here. So now let's say we're going to do some transient calculations. So if your case is steady, then you can select steady. If it is transient, if it is related to the time, then say this is transient. I'm not going to use the gravity for this case, but for many cases maybe you need to use the gravity. So but I'm not using the gravity for this term, so let's say it's transient. Click on this model. You can see we have different models here, like the energy equations, viscous laminar flow. So when it is particle flow, I discussed earlier, it is two phase, air is one phase and the particle is the other phase, so it's kind of multi-phase problem. So for the air is actually the continuous phase. So for the air, we need to solve some viscous model. So let's say we're going to use the K omega model and standard at all the other setting as it is. You can customize it for your problem. So for the air, we're going to use maybe the K epsilon model. Now we need to solve the particle. So particle is the secondary phase or discrete phase. So we have the discrete phase model here, DPM. So click on this DPM and then you will get this window. The important thing is, at first it will ask you whether you want to consider the interactions with the continuous phase. I said discrete phase, this is actually for the particle. Continuous phase is the air. So do you want to consider the interactions between the particle and the air? So definitely yes. We need to consider the interactions between air and particles. So select this. Once you will click this, and then you can see some what types of particle treatment, like the unsteady particle tracking or particle with fluid flow timers type. So if I select okay, I actually want to do some particle unsteady tracking and how I will inject the particle. So is it from the fluid flow time steps or the particle time step? So it's let's say the particle time step. Alright. Update the DPM source every flow iteration. So the default is 10. So maybe we want to update it up to every iterations. Okay. So this is the tracking parameters actually. This is important. If you want to know more about that, maybe you can just see the file now here. If I quickly tell you, this makes number of time steps actually related to the the particle calculations, the particle tracking, and it will help you to reduce the number of incomplete particle. So when you will run your simulation, this section, you can see this section, this is called the console. So in this section it will show you your calculation history, like how many particles you injected, how many particles escaped or reflect or evaporated or incomplete. So this max number of steps is 500, so you can increase this number like something like that. If you put this number a long number here like this, it will prevent you incomplete particle. So that's important. The particle time step size, okay, we will use just this 0.01 just as it is. Now we can select actually what sort of physical model we're going to use. So you see there are different options for the physical model. The subtract lift force, actually we need it for the Brownian motion, like for a smaller diameter particle. Do you want to see the erosions, like maybe you are solving some problem and the particle is hitting the wall domain. You want to see the erosion on that surface, that means where the particle is hitting. The two-way turbulence coupling, a DEM collisions. DEM, this is a discrete element method. So this DEM collision is actually the particle and the particle wall collisions, the interaction. So this is quite complicated, and I believe you don't need it right now, definitely not now. So the physical model, actually we can just keep this physical model as it is, because we already selected that we want to consider the interactions between the continuous phase and the discrete phase. So another thing is click on the injections. So if you click on injections, you will get this window, something like that. So you need to click on the create here. So if you click on create, then you will get this one, so it's something like that. So this is the injection name. So you can change this injection name, you can put any other name. And now the second question is, what is the injections type? There are different types of injections, like single means it will inject only one particle in a system. Group means a group of particle. Similarly, the surface means it will use the surface. Definitely you need to select which surface, and then it will use the surface mesh. So every face of your mesh, it will inject a single particle. So suppose if you have 1000 nodes, then your system will inject 1000 particle. So definitely we are going to use the surface injections. You can see different options. File, if you want to customize, if you have some special particle injection, then you can use the file. You can create your own file and you can just import it. So we are going to use only the surface injection here. Once you will see the surface injections, then it will ask you actually which surface, is it inlight, outlight, or wall. So definitely we want to inject from the inlight, so we selected that. So the particle type, this is the inert particle, and the material is anthracite. Okay, if you want, then you can use some others, like you can see different particles here, like the mercury, oxygen, oil, water, liquid, water vapor. So you can, so we're going to use the anthracite, right? The diameter distribution is uniform. That means we are going to use same diameter particle. So if our intention is we want to inject 1 micron, we will use 1 micron. But if you have any problem that you need to set some range of the particle, then there is another one. This is called the Rosen-Ramat distribution. So in this distribution, you will be able to put some minimum, maximum, and the mean diameter. So suppose minimum is 1, maximum is 10. So it will inject the particle in between 1 and 10. That's some random. So we're going to use the uniform particle. This is more accurate for our projects. So now we will check this. So they scale the flow rate by phase area. That's actually, it will calculate that mesh information from the inlet and inject using the phase normal directions. So that means it will go through the normal directions of the inlet, so from the phase to the normal directions. So that's, we will do that. So let's say we have the particle is 10 micron, and we will put the same time. You see the stop time, this is actually injection time. So we will inject the particle up to this. 0.001. So that's, and the velocity magnitude maybe this is 3 meter per second, and we'll keep this total flow rate as it is. Right, and then what is the physical model of the particle? So that's the drag law. Your particle could be spherical, it could be non-spherical. So if it is spherical, you can say it from here spherical. If it is non-spherical, then you can say from here. So that's the other thing, maybe I can discuss it later. What is the non-spherical? Today we're going to use the spherical particle. The turbulence dispersion is if you want to use any turbulence particle tracking, then you can select it from here. But especially for this project right now, I'm going to use this setup, not now, this turbulence dispersions. So I'll click on OK. I'll close this. I'll click on OK. So we have done with the the viscous model setup and the discrete phase setup. The materials, click on the fluid. So fluid, the material is air, so we are going to use the same value, so no change. For the solid, I think this is the aluminum, so you don't need to change that. For the particle, center side, you can change the density of the particle. It will depends like what types of particle you're using. So like say it's actually for this, like say we're going to use this density for this particle. So if you change it, you need to click on change, otherwise it will not change the value. For the cells and conditions, we don't need to do anything for here because we didn't change any materials, anything. Not boundary condition, this is important. So for the inlet, we'll double click on inlet, and now it will ask you about the velocity. So we'll put the same velocity for the particle and the air as it is, because the particles, it usually follow the air streamlines. So we're going to use the same velocity. Right, so we did it. We used the same velocity here, 3. So I will click on OK. For the interior, so there's, you don't need to do anything, there's the interior. For the outlet, if you want, then you can use the outflow outlet conditions or just the outlet conditions with the zero pressure. So here actually we need to change this. So this is currently wall, so if you just right click here, go to the type, and let's say this is pressure outlet, and for this pressure outlet we will put maybe the gust pressure, this is 0, or if you use the outflow, then you can select the outflow. So say the pressure is 0 there. For the outlet 2, we'll click on, just right click on type and the pressure outlet. Yeah, so this is the gust, 0 pressure, and click on OK. For the wall, this is important, the wall conditions. So it will depend on your problem, especially for this case. Let's say we actually want to see the reflection of the particle at the wall. So if you want to see that one, you need to go to the TPM, and then you need to select this reflect. And if you want to select the discrete phase reflections coefficients, you can put the constant value. Like let's say we are going to use the reflections, and then the normal direction is 1 and the tangential direction is 1. So 1 means it will be highest reflections, the particle will bounce with the maximum force, and if we put it in 0, that means there should be no bounce, no reflections. So and especially this problem, this is actually the first bifurcation of the human lung. The actual boundary conditions for this problem, it should be trough, but I think if you have your second assignment, you need to do some particle modeling with the reflect condition. So that's why I'm going to use the reflect condition here. So click on OK. Dynamic mesh is not important because we are not going to consider the deformation of this body, so that's not important. The reference value is just as it is. You can select the calculate formula, that's it. It will show you like your velocity and other parameters here. For the solution method, you see here, well, let's say we're going to use the cuckold, and the other thing I will tell you what is use the secondary arrow point I explained earlier. So use the secondary arrow point, and let's go to the control. So if you click on control, so then there is a flow current number. You can search it, what is current number, the relaxation factors, this sort of thing. I'm going to use the same values, I'm not going to change. But if you see an issue with your convergence, then maybe you can play with some of these values. So, and then the equation is there, we are going to solve like the flow and turbulence. So this is actually the first part of this video, and then to avoid the line, so maybe I will create one more videos. So from here, so this is the first part, and you will get the second part in other videos.